Mathematical models for epidemics describe how infection spreads through a population, say within a town or between cities and countries. Transmission can happen when an infectious person encounters a susceptible person, so mechanistic models of disease spread track infected and susceptible people and model their interactions. We are going to see a simple example of a transmission model and some of the general insights it gives into the spread of an epidemic and about ways to control that spread. There are different sorts of mechanistic transmission models. Detailed models account for individual members of a population and where they meet other people as part of their daily activities. For instance, contacts made at home, work or school, or during other activities in the community. We will look at something simpler, the Susceptible, Infected, Recovered model, the SIR model. This model just tracks the numbers of susceptible, infected, and recovered people, together with a description of the average number of contacts between them. This model divides the population into three compartments: susceptible, infected, and recovered people. Disease transmission can happen when a susceptible person meets an infected person. In our model, this moves that person from the S to the I compartment. Recovery moves a person from the infected to the recovered compartment. What happens to the epidemic can be understood in terms of the reproduction number, called R, which is the average number of infections caused by an infected person. If R is greater than 1, each infected person infects more than one person, and so the number of infected people goes up over time. On the other hand, if R is less than 1, the number of infected people goes down. A larger reproduction number means the infection has a greater potential to spread and is more difficult to control. R depends on the contact rate, how many encounters you have per day, the duration of infection, and the probability that an encounter would lead to transmission. If there are S susceptible people in a population of N people, the chance that an interaction is with a susceptible person is S divided by N. If we use the letter C to stand for the contact rate, D to stand for the duration of infection, and P for the probability of transmission when a susceptible person meets an infected person, we have that R is equal to C times D times P times S over N. The largest value of the reproduction number happens early during an outbreak when almost the entire population is susceptible. In that case, S over N is approximately equal to 1, and we have that R is equal to C times D times P. We call this value the basic reproduction number, R0 or R0. Combining the two equations for R and R0, we see that the reproduction number R is simply the basic reproduction number multiplied by the susceptible fraction. So R is R0 times S over N. Let's see what happens early in an epidemic when almost everyone is susceptible. Say the reproduction number is 2. Then the first person infects 2 people. Both of them infect 2, so 4 in total. Then those 4 each infect 2, so 8 in total, and so on. For each round of infection, the number of infected people doubles. This is an example of exponential growth. This exponential growth is illustrated in this graph that shows the increase in the number of infected people over time. Exponential growth cannot continue forever. Assuming that recovery from infection leads to immunity, as time passes in the epidemic, more and more people will already have had infection, meaning there are fewer susceptible people in the population. The reproduction number will decrease because an increasing fraction of contacts will happen with people who can no longer become infected. Just to say, this plot has a different scale on the vertical axis to allow us to see both infected and susceptible people on the same graph. Eventually, the fraction of people susceptible will fall far enough that the reproduction number drops below 1 and the epidemic declines. This is what we call herd immunity. The epidemic dies out not because there are no susceptibles left, but because there aren't enough susceptibles to sustain transmission. Notice that not everyone gets infected as the epidemic spreads. We see some people are still susceptible after the epidemic has passed. Having and maintaining herd immunity protects those people from the disease. A larger reproduction number means you need more people to be immune in order to have herd immunity. If R is 2, then you get herd immunity if half of the population is immune. If R is 3, then you need 2/3 the population to be immune. R is an important quantity to know because it tells you how effective control measures have to be to reverse the spread of an epidemic. Even if you cannot reduce the reproduction number below 1, any reduction will slow the spread of an epidemic. This is important because a rapidly spreading epidemic can easily overwhelm a region's healthcare system. So, if you reduce your contact rate, for example by social distancing, reduce the amount of time for which you're infectious, for instance by isolating yourself if infected, or reduce the probability that an encounter leads to transmission, so better hygiene or using face masks, you will reduce the reproduction number, slowing the spread of infection. This is what is called flattening the curve. These sorts of control measures slow the epidemic, reducing the peak burden on the healthcare system. But at the very same time, they make the epidemic last longer. Because the epidemic is slowed, susceptibles are getting infected at a lower rate, and it will take longer to achieve herd immunity. A stronger measure will have a larger effect and may be able to squash the epidemic. We have to be very careful about relaxing these sorts of control measures if we have yet to reach herd immunity. With many susceptible people in the population, we should expect to see the epidemic take off again. Here is an example where a stronger control measure was employed and then relaxed. The strong control sends the epidemic into decline, but then it was relaxed. Everything still looks good for a few weeks after relaxation, but then the epidemic takes off again in a second wave. It's important to notice that it takes a while before the effect of relaxing control is seen. That's because there is a time delay between a person getting infected and being reported as a case. Cases that we see now reflect transmission events that happened a while ago. There is an even longer delay if you look at data on deaths. What we see from this model is that control measures that don't give people immunity are only a stopgap solution. They buy us time until a vaccine is produced or a drug is produced that will make the infection less serious, or until a monitoring program can be put in place that rapidly tests, traces, and isolates infected people. They do reduce the peak burden on healthcare systems, which is an important consideration for COVID-19. While modelers are often the bearers of bad news, we can use our models to help design control strategies. While we don't have all the tools we might like, models can show us how to combine approaches such as social distancing, face masks, improved hygiene, and contact tracing to stand a fighting chance of defeating this pandemic.